So the talk is about this work that I do as part of the consultancy that I started this year, which is called Turing Meta, and it's a consultancy to help organizations to leverage biological science to actually solve organizational problems. So back in July, I gave a kind of lightning talk, and people seemed quite interested in it, and I kind of like outlined the rationale for looking at biology, because it's probably not obvious to everybody that biology would be a good place to start with organizational problems. But in the interest of time, I'm not going to go over the basic idea of like why I'm doing it. I'm going to jump straight in to kind of what that would mean. So that's what these slides are going to be about. And I apologize if I, kind of skate over that, but we can talk about it afterwards in terms of the basic, kind of rationale. So if you look at kind of late 20th century biology, there's this idea from Richard Dawkins of the selfish gene. And so it's this idea that from 1975, he published this book. It was a really big deal at the time. There was this big debate, the right way to understand evolution. And he was kind of seen as winning the debate, in the public debate at least, and probably also the scientific community as well, when he argued that the kind of selfishness of genes is kind of primary in terms of what drives evolution. And so one of the people that kind of did the basic research on this kind of idea was a guy named Bill Hamilton. And he talks about this realization that the genome wasn't this monolithic data bank that was just carrying out orders on behalf of a grand project to build a body and have birth, grow and have babies and so on. Actually, it was beginning to look more like a company boardroom, a theatre for power struggles, a place of egoists and factions. And so that's what you kind of got from late 20th century biology. And you notice the analogy with organizations is very explicit. So it's not something that is kind of a trivial connection. It's something that scientists think about in this way to help them understand the biological world. So if we go forward to 21st century biology, I attended this scientific meeting in 2018 by the Royal Society, and it's called Computation by Natural Systems. And so what 21st century biologists and physicists and computer scientists are starting to do is leverage the concept of computation as a way to understand the complex processes that biological systems are actually doing. Right, so what they're actually producing and how they do it. And we're able to do this because the way the science has moved on and the incredible level of detail, including like time series data that you can get now on biological systems, and that enables you to really understand them and use methods that we'd be more familiar with as computer scientists, but they're doing it with biological systems. And so scientists claim that understanding what nature computes is likely to help us in, to carry biology forward. But what you'll notice from this is that computation is a general model of work. So if you start coming up with models of computation for biological systems, you know that you can translate that into organizational problems, because the idea of a computer was originally just a person doing some work. That's what a computer was, right? And we just formalized it with mathematics, and now we take that for granted. But don't forget, this is a model of work, right? And it's work by any kind of rigorously defined work is a model of computation. And so when we translate biological systems into models of computation, we can take those same models and we can look at whether organizations also behave in the same way, and we can make comparisons. So now, instead of it being an analogy as it was in the 20th century, now it's something very concrete that we can actually do science with. So let's ask this question then. What do 21st century biologists think that natural selection is computing? What does it look like when you think of the work done in terms of evolution and natural selection? You get this idea that's emerging of natural computation, in the sense of computation done by natural systems, as a chimera. Right. So what I mean by that is this mythological creature, which had the head of a lion, the body of a goat, and the tail of a snake. And the chimera has become, like in terms of classics and stuff, it's a byword for something that's completely imaginary and doesn't exist. But in fact, it's also a great analogy for the kind of computation that's been done by natural systems, which is that they're overlapping computations. They're kind of entangled. So it's not the kind of computation that we're familiar with, the way we build computers. They're overlapping kind of models. And so if it's computing more of one thing, it's doing less of another. So an example of this discussed in that meeting was by a guy named Eric Deeds at Kansas State University, and he was applying information theory to cell signaling. So this is what you can do in 21st century biology. You can start to apply information theory to what cells are doing, right? And it wasn't really possible before, and it's just the start. And what he found is that the channel capacity of this particular signaling system, which was just designed, what we think it's for is for cells to self-destruct in an organized way. That's what we think this apoptosis is, what is programmed cell death. It's really important in understanding cancer because this is what stops cells that are precancerous going on to become cancerous. This is one of the important ways the body controls that. It realizes that a cell isn't healthy, and then it's the other surrounding cells send signals to basically tell it to self-destruct in an organized way without creating too much mess. And then the bits of the cell that are left over get used and repurposed by other cells. So it's a very efficient way to do that. But what Eric Dees found is that the message is quite unreliable. So the channel capacity is below 1 bit, which means every time it says, there seems to be enough molecules around, floating around, to say these cells should self-destruct, but they don't reliably do so. So he was asking, maybe this is like something else is going on here. It's not the simple story of apoptosis that we're expecting to see. And so what he found is that if there's some unreliability in that signal that's saying the cells should self-destruct, that would, if it was a very reliably, faithfully transmitted, you would get a big fluctuation in the amount of cells that are self-destructing, and that would be bad for the body. So it's an entangled computation, is how I would describe it. And what it's doing is it's computing the value of this cell should self-destruct and the value of the whole set staying alive. And so the two computations are being done and they're overlapping and they slightly compete with one another. And so this is what Eric Dees thinks is going on here. And it's an example of this chimerical overlapping computation. So how does nature resolve these chimerical kind of demands? First of all, you've got what I just talked about, organized programmed cell death, and this idea of the individual cell, the value of the precise dose trades off against the value of retaining the set of cells, right? You've also got evolution itself, and I haven't talked about this much, but there's lots of research by lots of different people to show that this idea of fitness that we're familiar with, survival of the fittest, kind of trades off against all these other things that are being computed in evolution. And these other things are kind of everything else that you would care about that's not simply efficiency, like reproductive rate efficiency. So robustness, innovation, cooperation under uncertainty, risk management, long-term efficiency, optimization in the long term, all these things trade off against efficiency. And so that should start to sound familiar to you working in an organization. Right? So this is where the analogy starts to yield some benefits. It's more than an analogy, it's the effect of looking at biological systems undergoing the same demands of human organizations. And so the solution to these chimerical functions looks like it's the computation of both sets and singular things at the same time. So that's like a general model of how these computations kind of are entangled. So now we're going to move on to organizations, human organizations. But before I do, I want to talk about this idea of the center of probability mass. And so this is just an idea from statistics that's got turned into equations. I think it's really important to understand the physical analogy that it comes from. And so the idea of a normal distribution, which is the idea that you see random things distributed in the kind of the bell curve in that way, it comes from Francis Galton, who was studying biological systems and trying to understand the variation. And he came up with this thing called a Galton board. And this is just a computer simulation of a physical board with some pins in it. and the balls are being dropped from the top, just like a kind of like 19th century fairground game, and they're hitting the pegs, and they randomly go left or right every time they hit a peg. But in general, there's more ways. If they start in the center, there's more ways for them to end up in the center than there is for them to get to the edges. And you end up with an approximation of the bell curve as a result. And so what are we supposed to take from this is that this is the property of a set, right? When there's more ways for something to happen than another way. And this is important in organizations because it's to do with what's the most prevalent or most likely thing to happen. And so most of the mass of things, of events that happen are where we want things to be in an organization. We want the most easy things to happen to be where most of the things are happening. The things that are more difficult to achieve, we want them to be, okay, they don't need to be so easy because we don't need to do them so often. And so this is a fundamental concept when you're computing sets. So let's look at an organization as a set of organizations. So this is the idea that this isn't one thing, this is lots of sets of things. And so first of all, you have this hierarchy, and you have these individual nodes, which might be teams or individual people. But these are these subsets, which is each circle there, is where you want most of the things to happen unilaterally, right? You want most of the things to be unilateral, and only one team needs to agree for it to happen. And that's where you want the mass of our action. And it's also going back to the probability mass. It's where you also want the most options for things to happen. So this is the other side of it, is the number of options you've got to achieve something. Now, bilateral action, where two teams work together, is also something where you have meetings, small projects, small strategic decisions. But within this existing organization, these larger circles are more natural bilateral action. And then you get less natural bilateral action. So these two teams are not so closely linked, right? So it's less natural that they easily work together. So we want the mass of actions, going by that principle of the Galton board, to be unilateral and with options. And then we want the remainder of that mass to be bilateral but natural, and so on, right? And so you end up with this concept of what a well-structured organization is by looking at the events. So you look at the events that the organization has to do, then you build the organization around it. And obviously this just explains that in a graph, a simple graph, that this is desirable, where most of the actions are unilateral because the laterality is just at the bottom. And this would be less, it would be less good if there are too many bilateral events that have to happen, and trilateral, and four teams working together, that would be less good. So like this is pretty obvious stuff, but it's good to start with the basics. And then it's good to understand that biological systems also work this way. If you've heard of irritable bowel syndrome, it's likely to be a problem that is caused by the lack of coordination between the upper and the lower gut. And it's to do with the stress response, probably being switched on and off too often. And it means that the upper and lower gut are not able to coordinate effectively. There's a lot of nerves in your gut, as many as almost as in your brain or something. It's a huge number. And it's like a second brain, basically, almost. And the need to coordinate the upper and lower gut is what goes wrong with IBS. And so you see in biological systems where the weaknesses are in the same way as human organizations. So now I'm going to talk about one of the effects on laterality of unnecessary precision. So if you see this Google Maps advert, Google Maps screenshot, you can see that there are 3 routes that are selected with one kind of highlighted. And by being less precise in what you're trying to achieve, you allow more options for it to happen. So the precision here is only the route within about 3 minutes of any route within 3 minutes of the best route is good enough to show. And there are 3 routes that are available within 3 minutes of each other. And that's like an objective for your organization. And these are the options you've got to achieve it. Now, maths basically is saying that unnecessary precision in your software requirements is going to raise the laterality of the likely result, right? Because there are less ways, there are less options to achieve precision that may or may not be needed. So like say you had a website that was available, needed to be available 99.99% of the time, right? So that's going to impact the laterality on your in terms of the events that you need to coordinate versus a website that's only available 99.9% of the time, right? So that extra 0.1% could be the difference between desirable and undesirable events in your organization. And that's not as probably natural to us to think about because we're not used to sort of questioning the objectives in a very organized way about what the effect of unnecessary objectives are. But this gives you a way to think about that and then actually have that conversation with the people who are setting the requirements to understand what the effect is on your organization. So if you look at something like this diagram is a C4 diagram, some kind of banking setup application. So we can start looking at software architecture in the same way. And you can look at different teams responsible for different things. So the database team might be different teams to the mobile app team. And so game theory in organization games, which I'll get onto, shows us that the unilateral actions are easier to achieve, natural alignment is important, and so you get that mapping with software architecture as well. And the whole idea of domain-driven design is to think about the organization, what the objectives are, what you're trying to achieve. This all maps onto that and is also based in biology. So it's a useful thing to kind of like overlay on top of your existing domain-driven design knowledge. Now I'm going to talk about natural and unnatural laterality of action. So how natural is it for two different components to actually coordinate with each other? And so we have this idea in game theory, which is effectively gives you that. And this is some slides I've borrowed from a guy named Bartolini, who is the, I think he works for the IMF, but he was presenting to the OECD, Organization for Economic Cooperation. And he was explaining how to get different organizations to work together using game theory to understand it. So in game theory, there are different games. So it's a mathematics of how people cooperate or compete. And there's a taxonomy of games. And in order of alignment, decreasing order, you've got pure coordination games, Battle of the Sexes and Prisoner's Dilemma at the bottom. And so the easiest ones to coordinate are at the top, the pure coordination game, and the hardest one is the Prisoner's Dilemma. So the way it works is that the simplest case is you draw a matrix. There's two people who want to coordinate, and you have your player one choices, A and B in red, your player two choices are A and B in blue. And you write in the matrix the reward they get for the combination of options. So for player one, let's say that if he chooses option A and player two chooses option A, player one gets a reward of 2. But if they fail to choose the same option to coordinate, they get a reward of 0. And if they both choose B, he gets a reward of 1. And it's the same for player two in this case, because this is a pure coordination game. So we write the blue is the same, player two's rewards in blue are the same as player one's rewards in red. And because their rewards are the same in each combination of actions, this is a pure coordination game. So this means that it's natural that they choose the same option because it's in both their interests to choose option A. But it can happen that it doesn't work out that way, right? Just if the flow of information is not good enough, then it can happen that they might choose A and the other choose B. So example, I say I want to play a game of sports with my friend Joe, and let's say that we both prefer to play football. I've got the football, he's got the goalposts. But let's say that normally we would just easily coordinate. But let's say I wrongly think that Joe prefers to play cricket, and because I'm a nice guy, I bring a cricket bat instead. And he does the same. He brings some cricket balls because he thinks I like to play cricket, even though I prefer football. We end up both choosing option B and getting nothing because we hate cricket, both of us, and we're just trying to please. That's a very English example. So in other countries, that would.
Oh, come on, man.
Anyway, so In the next one down, you've got called the Battle of the Sexes. It's got other names. You'll notice that in the matrix, they're not perfectly aligned. So in this example, basically two people want to meet. I want to meet Joe. Joe wants to meet me as well. But I would prefer to meet at my house. He would prefer to meet at his house. We're now no longer perfectly aligned. I get a slightly bigger reward if he meets at mine. But I can bribe him with beer and pizza in a similar way to get you guys here. So that way we all get to meet and we all get a reasonable reward. So that's what happens in this scenario, is that it's scope for negotiation. But you can see you might be compromising a bit to get what you want. So there's less natural alignment. So if you had different teams, you would be compromising, but at least you both are interested in the same set of options, right? Generally. In the worst case, it's called the prisoner's dilemma. And so instead of just A and B, we've got C and NC. And this stands for cooperate and not cooperate, non-cooperate or cheat. And this is meant to represent the risk that you basically enter into an agreement with somebody to do something, and then they actually get more out of it by agreeing with you to begin with, and then cheating and going back on it, and you doing all the work, and they get the benefit and none of the cost.
Just like renovating a house. Just like renovating a house.
Like renovating a house. Okay, yeah, that's a good.
Sometimes.
Yeah, I imagine it's pretty. I mean, it's pretty stressful anyway. But yeah. So this is the one that people talk about the most, the prisoner's dilemma, because of this problem. It's seen as very, very basic problem with cooperation, and the solution is generally seen to be contracts. It's like if people cannot be relied upon because it's not really in their interests, the idea is that a contract will solve that because it changes the rewards. They now get punished, right? It only works if they get punished. So then that changes the reward from 3 if they cheat to 1, and now it's in their interests to actually cooperate. Now you'll notice that at the moment contracts are quite a popular idea in some areas of compute. Now it's a good, it's a fine idea. It works in some situations, but it only works if you can actually punish people according to the concepts that we're talking about here. So, so with classical game theory, if we look at bilateral action, which is all we've been looking at, 2 people cooperating, this is like how you would want your organization to be. You'd want most of the problems of bilateral coordination to be pure coordination, and then a reasonable number that was left, most of them to be battle of the sexes, and only a small number to be the prisoner's dilemma. But what you actually see is that it can be worse than that. And some parts of the organization are likely to be towards that side because they're naturally aligned, and some parts of the organization are more likely to be towards this side. And so that's what you're expecting to see, right? Depending on how you architect your teams and everything. Again, in nature, you see this as well. So the selfish gene is not like an idle metaphor. It really happens that between the X and the Y chromosomes, there's some kind of war going on, right? Where they're basically antagonistic. And it's a fascinating piece of biology to understand the research that's going on here. But essentially, the male genes and the female genes are not perfectly aligned, right? Because it can be to the advantage of female genes to prevent males being born and vice versa, because that gives them more of an advantage in terms of their own gene. And so you actually see evidence of this happening even in the genome, right? And there's no jealousy, there's no people, there's no human psychology there. It's just maths, right? It's just maths to do with this. So it's a fundamental concept. However, there's an extra kind of like codicil or whatever to this, which is that having less options. So if you go back to the probability maths, if you have less options to achieve things, right, then things look like the prisoner's dilemma, because people cannot help you because they're too busy doing other things they have to do, or the choices are limited in how they can bend to what you need them to do. And so a pure coordination game, which looks at the number of options people has, can model this as well, right? And so having less options leads you to it looking like the prisoner's dilemma, and it's nothing to do with the politics or anything like that. It's just options. It's what options people have to cooperate with you. And so the ideal distribution looks more like this if you have more options to actually satisfy other parties within your organization. And so that's what I'm going to talk about next, which is the research that I've been doing on pure coordination games and options to actually coordinate with people. So if you think about architectural choices in software, what happens if you want to select the type of web server you're using? This can be looked at as a pure coordination game, or what I call an organization game. So this is the home straight now, so I'm nearly done here. But here is the concept of an organization game. Imagine Alice and Bob are having a conversation, and we're just interested in a pure coordination game where the payoff to both of us is the same. We're just assuming we get the same payoff. What happens is the game itself is changing. So the rewards are changing for both of us. To begin with, the best reward for both of us, we get the most out of it if Alice and Bob both talk. But over a bit of time, the reward could change slightly for both of us, and it might be better for one of us to stop talking and the other one to talk more. So, so then the new best payoff might be if Alice stops talking, Bob talks for a bit. And that's a natural way for a conversation to go, and then it can go back the other way. And what we're trying to do is keep our options alive to switch from one option to another as the whole thing changes. And the best payoff changes for everybody. And so we can think of a conversation as the simplest form of capturing this need for coordination. So how does this look like in terms of architectural decisions? If you, that's quite far away from me, so I can barely read it, but basically we imagine first of all the risk that the payoff to an architectural choice is changing. So let's say that we have a component and we have a choice as to whether model it as separately. So the model of what the business logic is separate to the JSON document. And in the second option, the JSON document is the model, right? So you have these two options. And if the specification of the business logic changes fast, then having a separate model is good because you change the business logic, but you don't have to separately go through the JSON document and update that. But if the change in the specification of the business logic is slow, then you're not getting much reward for that extra, extra flexibility you built into it. In fact, you probably pay a cost for the time it takes to make it. So we have two options we want to analyze, and there's two different ways that the game can change, right? There's two ways that the game can develop in terms of the reward. And so how we spend our budget depends on our confidence on what's the most likely thing to happen. Are the specification of the logic going to change fast or slow? And we can weigh different options, but at the end of the day, this has implications for lots of things in the, let's say, in the architecture. And in the end, we realize we have to go with this option. So for other reasons, we have to choose this option, even though it's got this risk that if the business logic changes fast, which is the first column, then basically it's in the red. It gives you a low reward. So this is the choice we choose. Now there's a risk. So in terms of the conversation, what I showed you before with the idea of this conversation, the value changing, we can see in this example of a conversation that the highest reward is if just one person is talking, but it doesn't matter which one. If one person stops talking and chooses that choice, the other one has to talk to get the reward. And so that's the basic idea of the option. When one person is fixed in what they can do, the other one can adjust what they're doing. And that's the basic idea of an organization game and what options you actually have to achieve that. So in this example, if the software architecture team has to choose an option that has that risk, you would hope that the legal team could reduce their exposure to that risk. Let's say that it's for an external party and the legal team is writing the contract. They can reduce the exposure to fast change in the terms of the agreement. And that is like this conversation. You keep everything alive that way. And so you've played this organization game. If the legal team is free and is communicating with the architecture team to write the correct protection into the legal agreement. And so it might be not a natural communication channel, right, between the legal team and the software architecture team, but it could turn out to be important. And so This pure coordination game looks like a way of efficient communication and options, allows you to conserve that flexibility of the organization and avoid getting into the stereotypical idea of the prisoner's dilemma, where you're just assuming teams do not want to work with you because they're not aligned to you, right? There's this underlying thing of options happening. And so if you play that pure coordination game, you can actually have a far more constructive conversation than classical game theory would lead you to believe. So you can change this kind of distribution in your organization, in which if this is because there are fewer options for each team to accommodate the others, you want to switch to a situation where there are more options. And that leads me back to what I said before about the objectives, where people are setting requirements. Is it worth hemming people in, to hit an objective, or is it worth communicating to give people the options and communicating how valuable options are and the probability mass of the organization is going to be conserved, and you have more ways to achieve things. So in conclusion, to kind of wrap it up, there's this organic organization. I'm calling it a manifesto. Feel free to sign up. There's nowhere to do so, but we believe the organizational trade-off demands solutions that compute sets and options, not just singular kind of target forms. So we predict the transient organizations, the subsets of the organizations, and we're interested in predicting the future and predicting architecture changes. And we're interested in developing scenarios using both classical game theory and organization games. So we train organizations to play pure coordination games and make that part of the culture about information value, the value of adaptation, and conserving options. So that's what your organization would be doing to play this game better, if you like. And we figure out many ways to do things over the one best way to do things and sets of options over single answers. And we model value indicators for architectural development in different scenarios so that we can play this game more efficiently and communicate better. And we believe that biology tells us that this is what makes reliable complexity and effective cooperation actually possible. This is what makes it work, is these options and conservation of probability mass. And the takeaways for this is, and we'll hopefully have time for questions, is to ask yourself what organizational problems you see in terms of your organization and the way that you've got your current architecture, and how they're best solved. Are they best solved by reorganization so that what was bilateral is now unilateral? Is better incentives partly make a big difference, like with the battle of the sexes, or better objective setting, or such as removing unnecessary precision, better information sharing, better negotiation? All these things could be important, and the ability to play coordination games. And that is the end of my talk. And hopefully I didn't drone on you too long. Yeah, no. So now it's the questions. Yeah, go for it.
Right, very nice presentation, by the way.
Thanks.
In terms of the game theory, do you think that, let's say if you take companies as a context of game theory, whether companies do tend to follow game theory, or sometimes there can be somewhat debacle or disaster sometimes?
Yeah. Well, there's this idea.
I'm trying to get
there's an idea that people who think that they're just using their own common sense and their own intelligence and awareness of how things work, they're normally very, very reliably parroting almost verbatim the ideas of a long dead philosopher, and it's normally Adam Smith or somebody related to Adam Smith. So you've basically got these ideas already happening in the organization. Everybody uses the psychology. They're familiar with the psychology of game theory. Everyone's familiar with the idea of politics, and it's not in their interest and I have to bribe them, right? So there's this stereotypical way of doing it without turning it into maths. But what's interesting is how it relates to things like options and this deeper substrate of things that are actually going on that's not about psychology. It's just about, as I say, options and how those things work. And that's what's really interesting to me. So hopefully the takeaway from this is not let's run away and figure out who's my enemy in my organization. Cheating, that's not what I'm going for. I'm trying to, a lot of people put a lot of work into getting away from that, actually, in terms of biology. We started off in the late 20th century with that idea taking over selfish gene. And we're spending a lot of time almost undoing all the assumptions underlying that. So that's what this is about.
So Evans has a number of different models: bilateral relationships, conformist, anti-corruption layer, consumer supplier. Have you thought at all about how your game maps to those different types of bilateral relationship in domain-driven design?
Yeah, it's not my model. So game theory is like it's definitely not. It's an economist's kind of like, you know, it's an undergraduate textbook, you know, module for an economist, and you know, probably A-level economics, although I didn't do it. But yeah, I mean, there's loads of research on game theory in terms of lots of different, you know, parts of the economy and stuff. It's surprising how little it's actually talked about in organizations, I would say, because a lot of it focuses on academics in sort of, yeah, I mean, it's a huge topic, right? Game theory. So people have looked at it, as my answer. We've definitely looked at it, but I don't know whether I could point you towards.
I guess thinking about it, that if you thought problems, a chance of a conflict or somebody changing their point of view, you'd go with a more contractual type of relationship, because you'd want to lock that down, you know, early on in order to.
Yeah. I mean, you know, what's interesting to me is how this stuff like what people figure out on the ground is more interesting almost than what the academics are saying on it. And it's putting the two things together to actually have a more constructive relationship between the academic point of views. Because if you ask general economists about things, they'll say contracts are incredibly important, you know, for achieving things, anything and locking things down. I think that locking things down in a contract is a great way to lose options, right? So what you want to do is achieve trust and then avoid the contract. The contract is like the last resort. It doesn't really solve your problems, because by forcing people to do things that they don't really want to do, it's like a kind of competing heuristic for kind of trust. And there's a reason why trust is valuable. And there's a reason why the prisoner's dilemma is almost intractable, right? It's because when you lose trust, the options disappear, because if you try to lock everything down, you can't move. So that's the problem, right?
Do you actually think that in that sort of point you just made, do you actually think that, so that means that having a contract seems to be like a self-fulfilling prophecy in the sense that, for example, in that the trust yet any sort of is being reached between two parties, okay, is basically the trust is being eroded because of the contract. Do you think sometimes?
No, definitely. Yeah. Once you get into that frame.
Or maybe I'm wrong.
Yeah, no, it can be, definitely can work, end up being that way. You know, I mean, it's you know, yeah. So the point is not that the classical game theory is wrong. It's not wrong. It's right. It's that it's incomplete. And so what I'm trying to do is balance the models so that you have two models that overlap, these overlapping computations, and make you aware that these two things, there's two ways of looking at it. And then you actually see the whole thing, the dragon, if you like, rather than being biased just to look at it one way. And that's the trick, I think, with this, is that balance. Yeah.
Thank you. Very nice.
This one tends to be that these concepts, in an interesting way, is that these are with concepts that have existed for a long time, a relatively long time since computing, right?
In theory, yes. Yeah.
Or just, for example, with the unilateral concept, you have individual components that are computing their own without necessary communication with other components. And as you become more and more depending on other services, you have like a shared kernel, something that you want to get away, right? Like the unnecessary precision, right? As in, like, you cannot foresee requirements in the future. Therefore, like, why are you going to do that to yourself? Technology and best practices tends to be very easy in a sense because they're all very heavily documented. The successes in regards to companies that have applied these principles and practices. Biggest problem I always find, it's very difficult to get a surefire answer on, is the people. People are always the biggest problem, and having to get people on board with these. And how does this resolve to, you know,
Yeah. I mean, well, if you look at my other talk, which I recorded a couple of weeks ago, you'll see I talk about people going into a hierarchy and how that's the biggest thing that changes the hierarchy is the people that are actually in that position.
Yeah.
The hierarchy isn't the organization, it's the people
That's
in
correct.
those roles, however that works. And then, you know, that's interesting as well. Yeah, it is a sort of bit of another topic.
So basically, given an example, a real one where, you know, say, for example, you have a scale up that is, you know, expanding. And so you tend to find this is a natural breeding ground for people that get in early, tend to rise to positions that maybe they are, maybe their performance would not be adequate for that level of position. And therefore, the entire organization becomes constrained to this individual, the decisions that they make. So, you know, it becomes a challenge, you know.
Yeah.
And when you have to try and onboard people on best practices and principles, and how does it resolve to like actual people? Because people tend to be the hardest part.
Yeah, well, the organization, essentially any organization that you end up with is not the right organization. So this chimerical model is telling you that organizations don't have a single best solution. There isn't, it shouldn't be a lion, it shouldn't be a snake, it shouldn't be a goat. It's a mixture of all three. So whatever organization you choose is going to have drawbacks. And then the thing that makes it more scientific is to say, these are the predictable drawbacks of this organization. And these are the ways the behavior is going to compensate for the drawbacks of that default way of working.
Yeah.
That's what makes sense to me. That is how you would work.
Yeah.
I actually see that in biology. That's how it actually probably works in biology.
Going back to your game of collaboration, when you said the example about you and your friend choosing between playing football or cricket, said that if you both choose to play cricket because you think the other prefers cricket best, you get nothing. But I disagree with that because you get to you both choose the same and are able to play cricket. So after all, you get something. You would get nothing if you would choose differently. One chooses to play football and brings the football goals, and other plays the pass.
It was a slip of the tongue. In the actual matrix, you do get a reward for both choosing the same option, whatever it is. But you don't get as high a reward for cricket as you do for football. It's on the matrix, but I probably said it wrong.
What I mean is by you both choosing cricket, you would both be choosing option B, so you get the lesser reward, but better than choosing different.
But
Yes.
at least you would learn a new game basically instead of football, is it?
Arguably, someone would have to know the rules. But yeah.
If I understood correctly, one of the takeaways was that the more options you provide or that exist, the better. But I'm wondering how that conflicts with the fact that the more options, well, you can end up with this analysis paralysis, you know, like too much to consider and you end up doing nothing because of that.
Yeah, lots of architects talk about, I think I saw working in the first derivative or the second derivative or something, and it was this idea about conserving options as choices. So basically, you make a choice that conserves the most options. And so what you see in biology is that a lot of complexity probably results from biological systems doing the same thing. And so you don't have to look at this stupid options theory, which doesn't make sense for organizations. You can look at biology and you can look at the work of someone like Alex Visner-Gross and his paper on algorithms that conserve options, basically. So you're making choices, but those choices give you options going forward. And so it's a bit like typing on a keyboard, and you know, like the spell checker is saying, or the predictive text gives you words it could be, and sometimes there's a lot of words and sometimes there's less words. It depends what you type. You want to be typing something, producing something, and it keeps suggesting words that you can write next, right? If you write too many words that are very obscure, you can't complete that sentence. There is no sentence that finishes that way. And so instead of thinking just in terms of this is my objective, I have to get to my objective, you should be thinking of what is passing the baton to the team after you leave the company. What options do they have going forward? right? So it's it's just thinking ahead to the options that you've left, not paralysis, because you're still building, right? Still typing. But yeah.
Can it be also said that sometimes going for the more general approach or one that offers more options?
Yeah.
Tend to be a negative consequence where you may want to be highly coupled or very specific to a cause, for example.
Yeah, so this is the advantage of this approach. When you tie it more sort of mathematically, it's not merely like a heuristic. You can give all the context where it works and where the sort of like counterexample actually proves the concept. So it can definitely make sense to be more tightly coupled, right? And you can understand that because one of the things that happens is if you change this, it breaks that. That can actually be good because it communicates very effectively that the change needs to be made. Whereas if it didn't happen, you might never know unless you do some complicated test, right? So that's fits nicely in a mathematical model, right? Where you're looking at how easy is the bilateral, how natural is it? So that fits with that concept of naturalness in terms of communication flows. So if you go to a pure coordination game, it's just about how efficiently information flows. So breaking things is efficient flows of information, just like a grammatical mistake on a parser or something's inefficient, you know.
So it's always, it depends, yeah.
Could I ask, where could we learn more about this? Quite fascinating.
Well, on my website, Turing Method, you find many.
Oh yeah, I can't see it properly, so
Yeah,
I'll get after.
I haven't written a book. These books are available in all good bookstores, I think, but you would have to piece it together from these books. So what I've done is like the whole point is that obviously when you do like a literature review, you read a lot of different papers, they're all fascinating, and you have to put it all together.
Yeah.
And that's obviously what I'm doing on the website. If you read these books, you'll find why am I reading this book? And that's the problem because the information's in there, but it's not obvious, you know. And so that's the work that I've done is to make it more clear, you know.
Well, at least you've enlightened us this evening. Thank you.
Well, thank you very much. It's very nice of you to say.
Sorry, it was bilateral and the other option was? You
There's
said-
unilateral,
Unilateral.
and trilateral, and you can you can try. I don't know.
Is that a model that fits any organization size, or is there an optimal amount of people or teams within that organization? This works the best?
So this is the thing, this research is not really based on organizational management science. It's based on biology and translating it into, so it's translational research. So I don't have like lots of papers that I've been reading about organizations. I do read about them and there are papers that I pay a lot of attention to, but not forgetting the stats, if you like, for these things. Because I'm trying to come up with models that work in biology and organizations, because I believe that's the right way to make progress. So people come up with a ready-made model, it's very specific to a human organization, so you can't translate it.
I mean, in biology, for example, a bigger organism, I think is for longer, but it's not that efficient internally, like in terms of things that can do, and the other way around, a small organism.
There's lots of different dimensions to consider when you look at things like longevity of an organism. You've got single celled, you've got multi-celled, you've got like obviously you know, you've got the metabolic rate of the organization. So mice have a similar different metabolic rate, but similar number of heartbeats in a lifetime to an elephant, right? But obviously because their heart's going faster. So there's some very interesting kind of laws that seem to govern the longevity of organisms regardless of their size.